So I thought I should do a video on subtyping. This is problem set 8, right? So the problem set itself has a lot of information about subtyping, but it probably doesn't introduce subtyping in a very easy manner. There is a lot of reading material which should provide you the context, but I thought I should still do a video to explain what's going on in all of the syntax, right? So what is subtyping? So if you've done any sort of object-oriented programming, you would know that um, object-oriented programming has this idea of superclasses and subclasses. So, for example, let's take the real-world example of something like you want to classify animals, and each animal is an object. Um, and you can sort of imagine this hierarchy where you have all sort of animals on top, and then below that you have classes of animals. You have felines and canines, and below that you have individual animals which are cat, tiger, dog, and wolf, and so on. So each of these are classes, and you could have multiple objects that belong to each of these classes. You can sort of think of classes as types and objects as values belonging to that type. And now the idea of subtyping is that you could have a particular function or a field which works on all animals. Let's say all animals have some field called name, right? So if animal has a name, then feline must have a name. Any object of the kind cat should also have a name. So we call this relationship between superclasses and subclasses to be subtyping. And we in programming languages we tend to use this particular symbol as the symbol for subtyping. So what you see here is the class hierarchy that shows the superclass subclass relationship between all of this, but it also shows the subtyping hierarchy. And in particular, you can see that when we write something like this, it says that cat is a subtype of feline and feline is a subtype of animal. And wherever you expect an animal, you can always pass an object of class feline, because everything that is expected of an animal is satisfied by feline. And similarly, anything that is expected of a feline is satisfied by the cat, right? So the thing on the left in O is called a subclass, thing on the right is called the superclass. But in this problem set, we are going to study subtyping in a functional setting. In particular, we are going to extend simply type lambda calculus with the tuple type. Tuple type is what you've seen in OCaml and Coq, right? It's essentially pairs and triples and so on. But here we are just going to consider pairs. But it's a very special kind of pair. In particular, it permits both depth subtyping and width subtyping. We will see what these are. And you are asked to prove the type soundness of this extended language. That is, well-typed programs with subtypes do not go wrong. Actually, to be very precise, do not get stuck. Where the meaning of getting stuck is the same as what we had seen in the lecture. Okay. All right. So let's go into the details now. So here is the Coq script. Okay, so what we have here, we have the usual variables, abstractions, and applications. So we've in simply type lambda calculus, we had natural numbers and operations on natural numbers. We are going to drop them, and instead we have variables, abstraction, applications, and we have tuples. And we have a nil tuple, tuple cons, and projections. So in order to make it easily readable, I'm going to use a special syntax. So the syntax is going to be this. So I'm going to represent empty tuples with a null. tuple cons with a pair like this, and projection is given an expression. You can ask for the nth element from that tuple, and this expression must be a tuple, and this will be enforced by the type system. And our values are lambda abstractions. Um, I also use the same empty tuple for in the value as well as the type. The context will be clear, right? So I'm not going to make um, the distinction more obvious. So this is empty tuple value, and this is empty tuple type, right? And we have values which are also tuples where the first component must be a value, and the second component must be a value. Then the whole tuple is a value, and this is precisely what is conveyed here. So tuple nil is a value, right? And tuple cons is a value. If e1 is a value and e2 is a value, then tuple cons of e1 and e2 is a value. Okay, so that's the syntax. So what are the expressions that you can build um, with the language that we've just seen here? So in this extended language, an empty tuple is a valid expression, right? This is a tuple with two values, right? And the first value is an abstraction. The second one is an empty tuple. That is a valid expression. The thing to note here is whatever is here is a type. It can be any type. Whatever is here in the second component must be a tuple type. And similarly, this is a valid expression. It says uh, given this tuple, which has one element, get the element at position 0, right? And this is also a valid expression. Here, first one is a sum type, right? This is an abstraction expression of type abstraction. The second one is a tuple type, which is recursive, right? So this is an abstraction, and this is a tuple value, and I'm extracting the element at position 1, which should be this identity function lambda y dot y. Okay, so we've seen valid example. Here is an invalid example. So this particular expression is invalid because our expectation is that when we construct these tuples, the first one can be of any type. The second one must be a tuple type, right? But this is not a tuple type. This is a function type. This particular expression has a function type, not a tuple type. Okay. So the operational semantics for the rest of the languages, I'm going to skip substitution, context, and plug. You can follow it along. There is nothing interesting going on. In terms of operation semantics, there is beta reduction, there is projection 0 and projection S, right? This is, and what is the meaning of this? Projection 0 says if given this expression where first one is a value, second one is a value, and you want to uh, project the 0th element, then the thing that you get using step 0 is V1. V1 is the first component, right? And if you have some V1 comma V2 and you are trying to extract the n plus 1th element, then step 0 says you would extract V2. The thing that you get is V2 where you extra project out the nth element, right? So you've thrown away one layer of the nested recursive tuple. This is no different from what you will find in OCaml, right? So something like list.n in OCaml does the same thing, and we're not doing anything more interesting than that. So that is expressions and semantics, right? What about types? So the type definition is going to be here, right? So we have the function type, and then we have the tuple type for nil and tuple type for cons. So here is um, sorry, this should be, sorry, this should not be a type, but what this should be is, this is a tuple expression, right? And this is a tuple value, and these are the same thing. And I'm going to use the same symbol for the types as well, right? I'm going to mark this as empty tuple type. And the only expression that has the empty tuple type is the empty tuple value, which is also represented by this null symbol. And you have a pair of tuple types, a tuple cons, where the first one is some type and the second one is some other type. And particular, we will see that the types are restricted in such a way that the only thing that you can construct here is considered here is a tuple type. Okay, so that is the types. What are the typing judgments? So if you will skip subtyping for now, we'll come back to it. So let's look at hash type nil, right? So under any context, tuple nil has tuple type nil, and this corresponds to this tuple nil definition. Under any context, the value, this one is the value, right? So this is um, sorry, tuple nil value, and this is tuple nil type, right? So under any context, if you get a tuple null value that has tuple null type, and what about pairs? Um, if you have a tuple cons expression E1 and E2 that has type tau1 and tau2, if under the same gamma E1 has type tau1 and under the same gamma E2 has type tau2, okay. And the third rule is a bit interesting. So this covers tuple nil and tuple cons, and the rule for projection is quite interesting, right? So the trickiness here is we are going to extract the nth component from an expression, and we are going to get some type for this, right? The type is the type of the nth component in this particular expression. So what we say is under a gamma, if you project the nth component from an expression, then it has the type tau. If under gamma, E has some type tau prime. So this is like an existential variable, right? So tau prime does not appear here. So E has some type tau prime, and we define this type level projection. So if you get the nth component of this tau prime, then that is going to be tau, right? This is quite strange. What is the definition of this? This is very similar to what we had done for expressions, right? So if you have type tau1 comma tau2 and you want to extract the 0th one, then it will be tau1. And if you want to extract the n plus 1th element from tau1 plus tau2, this is the same as extracting the nth element from tau2. So what does this correspond to? This corresponds to the projection rule here, right? And this proj underscore t prime nt, right? The definition here corresponds to type level projection that I have. Right? How does it correspond here? So you can see that if you have a cons, tau1, tau2, 0 gives you t1. This is what I have here, right? If you have type level tuple cons, then if you extract the 0th one, then you get tau1. Okay, so let's look at an example of how to type check a particular expression, right? So this is the type derivation tree. So I'm going to start from the bottom, right? So I've sort of filled the entire tree, but you can start at the bottom. So I'm going to say this particular expression is a tuple, right? So this is a tuple. where the first expression is an identity function. The second expression is it should be a null. The second expression is going to take it's the second expression is also a tuple, right? So the second expression is a tuple. We need one more bracket here. The second expression is a tuple. Um, sorry. Yeah. So what you have here is that this expression is a tuple, right? And the first component of that is a function that takes some y, right, and returns a tuple expression, right, with y as the first component and null as the second component, an empty tuple as the second component, and the last one in this recursive outer recursive one is a empty tuple null. So this is you can think of this as a tuple that has two expressions, right? This is the first expression, this is the second expression, and this is like the nil element of a list, right? And I'm going to get the first element, which will be this particular expression. That is what it's going to project out. And what's the type of that? I'm going to say the type of that is it's going to take an empty tuple because we don't have polymorphism in simply type lambda calculus. I'm just using the one base type, which is the null type here, nil tuple type. So I'm going to say why this particular function is going to take a null tuple type, and it's going to return a, tuple expression with null, comma null, right? So that's the type of this particular expression. How do we type check this? So the way you do that is for type checking projection, you have to apply the projection rule, which says that given this type, you have to come up with some t prime, right? Um, which would be the type of this expression E. And then given that t prime, extracting the nth element from that would give you the type that you're looking for, the tau. Okay, so we have to come up with that type for tau prime. What's the type? I can give it this type, right? The type is going to say, for this identity function, I'm going to pick um, uh, null tuple to null tuple, right? And for this expression, we know what the type is. That's the tau type. And this nil tuple expression has del tuple type. Okay. And extracting the first one from this should give you this type, right? Which is the same as this type. And this exactly corresponds to what we are looking at here. Okay, so now how do you type check this one? So this is a expression which has a pair of types, right? This is cons, tuple cons. So this is the first type, this is the second one. And if you look at the rule for that, it's going to be this one, right? If you have E1, E2, and you want to show that that has tau 1, tau 2, then independently show that E1 has type tau 1, E2 has type tau 2, which is what we do here. I need to show that this first component has lambda xx as type nil to nil, right? And this tuple expression has type this particular type. Right? This is going to be easy, right? So we just apply the abstraction rule here. So assuming that x has type tuple nil, then x has type tuple nil. So this one works through, right? This is just the variable rule at this point. We've seen variable rules already. And for here, we have to do one more unfolding of this tuple cons, right? So extract the first one right here and the second one here. This is easy because this would be tuple nil, right? And for the second one, there's a lambda here. And when you have a lambda, you assume that y has type the argument type, right? And given that assumption, this particular expression should have type nil nil, and it does. So how do you type check this? This is again a pair. So you have to again apply the rule triple cons, right? So you have to show that under this context, y has type nil, and under the same context, nil has type nil. So this would be satisfied with triple nil, and this is a variable rule. Okay, so given this proof tree, we can show that this particular expression, this particular expression has this type under an empty context. Okay, I will stop here and continue with another video.